Hello viewers and welcome back to this channel. So in this video we are going to be handling trigonometric graphs. So this is going to be our fourth video under the videos under electrochemistry. So this video is presented to you by Yusuf, and you advise subscribe to the channel and share the video to your friends so that we can all benefit together. Now when you're looking at conductometric titrations, we are going to be looking at graphs. But these graphs are going to be between an acid together with a base. So we are going to be looking at different scenarios. We are going to look at a situation where we are having a strong acid and a strong base, such as sodium hydroxide as a strong base and also hydrochloric acid as a strong acid. And we are going to see how a titration graph can be plotted when you try to titrate one against the other. So you're going to be looking at different circumstances. We are going to be looking at when the strong base is being added to the acid, and we also look at the situation when the strong acid is added to the strong base. So we are going to be doing both scenarios, but here we are going to be specifically looking at the effect of adding either a weak acid or a strong acid to a weak base or a strong base. So in number one, we are going to start with a strong base against a strong acid. So when you say strong base against a strong acid, that means that we are adding a strong base to a strong acid. So our graph is going to be, in terms of conductivity, is going to be on your y-axis, and then what you're going to be adding is going to be the strong base, which in this case is going to be sodium hydroxide solution measured in centimeters cubed. So according to the graph, it's going to be looking like this. Now you're going to notice that most of our turning points are going to be called the end point. And just like we described earlier on, the end point is going to be that point where all ions from an acid are being neutralized. So you should know that. But just like we are dealing with conductivity, it's important for you to know which ions conduct or have the highest mobility. Remember, the higher the mobility, the higher the conductivity. So here it's in order. So hydrogen ions have the highest mobility. That means that they have the highest conductivity. Then hydroxide ions are the second in the list, and these ones have relatively moderate mobility. But hydrogen ions have the highest conductivity since they are the lightest, followed by hydroxyl ions. So in these graphs, you're going to be looking at the change in the conductivity of our hydrochloric acid as we are adding sodium hydroxide solution. So let's look at the explanation of the graph. So we're going to say that initially, which is at point A according to your graph. So initially, conductivity is high, and this is due to presence of very many fast moving and highly conducting particles of the hydrogen ions, which are coming from the completely ionized hydrochloric acid. Now, just like I said, the highest mobility ions we are having are going to be hydrogen ions, and hydrogen ions always come from the acid. So if you look at this point initially at point A, it means that here we are having zero concentration or zero volume of sodium hydroxide that has been added. So that means that most of our solution is mainly the hydrochloric acid. Now, since hydrochloric acid is a strong acid, it fully ionizes in solution, giving us the hydrogen ions together with the chloride ions. So these hydrogen ions that are released, I say that they have the highest mobility. So since we're having a lot of the hydrogen ions in the solution, we expect conductivity initially to be as high as possible, since they are the only ones present in the solution. Now, just like we have seen on the previous slide, you have seen that on your graph, conductivity is rapidly decreasing, or it's simply decreasing along line AB. As sodium, remember that your graph is again a sodium hydroxide, so that means that the more the graph slants this side, that means that the more sodium hydroxide we are adding. So as we are adding more sodium hydroxide, you have noticed that also conductivity, which is on this y-axis, is decreasing. And the reason why it is decreasing is due to the addition of sodium hydroxide. Now this is because remember that initially we only had fast moving hydrogen ions. Now as we are adding our base, the hydroxide ions that are going to come from our base, they are going to come and neutralize the protons which were causing this high mobility. And if that is done, that means that we are reducing the conducting particles in the solution, and therefore mobility of the ions within the solution has also been decreased, which in turn decreases conductivity. So also in this statement you're telling you that the decrease along AB due to additional sodium hydroxide is because your fast moving and highly conducting hydrogen ions are being neutralized, and they're being neutralized by the hydroxide ions that are coming from the sodium hydroxide solution. So making an equation for that, you write hydrochloric acid reacting with sodium hydroxide giving you salt together with water. But simple ionic equation is going to be the hydrogen ions reacting with the hydroxide ions to give you with water. Now remember that water is simply a molecule, so it's not a conducting particle. That's why conductivity tends to decrease. But also remember that also the salt that has been formed, sodium chloride, in ionic chemistry we say that all salts are strong electrolytes. So sodium chloride as a salt fully ionizes to give us sodium ions together with the chloride ions. Now also these ones are conducting particles. Also these ones are conducting particles, but for them their conductivity is very less since these ions are heavy in solution. Now since they are heavy in solution, that means that their mobility, the way they move in solution, is so slow. That means that also conductivity is going to be at relatively lower value. Now when we explain our turning point, which is the turning point B, which is called the end point, we are going to say that conductivity here is low, and this is due to the sodium ions together with the chloride ions that are being formed from the sodium chloride salt formed. So at the end point is the point where full neutralization happens. If you're adding a base to an acid, that means that all the hydrogen ions of an acid are being neutralized by the hydroxide ions from the base. So what you're going to have in such a solution, you're going to have your salt as above the according to these equations above. So you're going to have your salt together with water as a molecule, but water is a non-conducting particle. But the salt that is being formed at the end point is a strong electrolyte, therefore it undergoes full ionization to form the respective ions, sodium ions and chloride ions. But these ions do not have a high mobility because they are heavy in solution. Their mobility is low. That's why also the end point is formed at a level where conductivity is low, because these ions that are coming from the salt, which is sodium ion and chloride ions, they are not that light, so they move very slowly in solutions. That's why end point is got at a very low conductivity. But always at the end point, conductivity is going to be due to formation of the salts, even for other graphs that you're going to be looking at. So we look at the rise, which is going to be from B to point C. So along BC, conductivity is increasing, and this is going to be due to excess sodium hydroxide that's being added. And you are going to frame that in terms of a statement, and you're going to say that conductivity is increasing along BC due to the increase in the concentration of sodium ions as we are increasing the volume of sodium hydroxide being added. Now remember that after the endpoint being reached, that means that all the hydrogen ions were neutralized. So the excess sodium hydroxide that is being added is going to fully ionize to give us sodium ions together with the hydroxyl ions. And I've already told you that hydroxyl ions are the second mobile ions apart from protons or hydrogen ions. So the addition of sodium hydroxide in excess provides these hydroxyl ions that are responsible, that cause high mobility in that solution, hence increasing the conductivity. And that's the simple science behind that. So it's increasing due to the addition or due to the increase in the concentration of the fast moving hydroxyl ions that are being added. Now you're going to make a note that the volume at the end point is going to usually be obtained by extrapolation. We are making this note just in case you are required to show the data that has been given in the table on a graph. You always get your end point. Let's say that you have plotted your points on the graph in this format. Now as you're plotting your graph, you always find that your graph is going to go in this shape. Now for you to get your endpoint, you're supposed to get your ruler and extrapolate this. You also get your ruler and extrapolate these points. So where the two lines meet is going to be your endpoint. That's why we are telling you that the endpoint always, whenever you sketch the graph, is going to be got by extrapolation in case you have plotted your graph when provided with tabulated data. So you're saying that the point where the two extrapolated lines meet is going to give you your endpoints. I hope that is understood. Now for the second item, we are going to be looking at the titration of a weak base against a strong acid. So that means that we are adding a weak base to a strong acid. Now just like we said, the initial point for a strong acid is going to be high because strong acids always fully ionizes in solution. So for example, hydrochloric acid, strong acids free ionize in solution. That means that they give us excess of the hydrogen ions, and I've told you that hydrogen ions are the highest conducting particles in the solution, followed by hydroxyl ions. Other particles tend to be relatively heavy. Their mobility is low, therefore their conductivity is always lower. But for when you're having a solution having excess of the hydrogen ions are very light in solution, so their mobility is very high. And once the mobility is very high, that means that also the conductivity is going to be high. So if you are to explain this graph, you are going to start it like the previous one. So you're going to say that initially conductivity is high at A, because at A we are having very many fast moving and highly conducting particles of the hydrogen ions, which are coming from the completely ionized sulfuric acid. Now you change this. Now for this example, you're using sulfuric acid, any strong acid. You just have to know that all strong acids fully ionize in solution, and when they do so, they give us excess of the hydrogen ions. Hydrogen ions have the highest mobility in solution because they are very light and they are fast moving ions. So since they are very light and they are fast moving ions, we expect them to have the highest conductivity as compared to any other ions. So you're going to look at this gradual decrease. We are going to look at this gradient decrease along line AB. So the gradient decrease along line AB, you are seeing that is due to addition of this ammonia solution. But remember that ammonia solution is a weak base. So here we are going to say that conductivity is decreasing along AB as ammonia solution is being added simply because now here the conductivity was high simply because you had a lot of hydrogen ions, and conductivity is decreasing along AB because as you're adding ammonia solution, ammonia is reacting with your sulfuric acid forming ammonium sulfate. Now once that happens is that the fast moving hydrogen ions are being replaced by very heavy ions, which causes a decrease in the conductivity. So you're going to say that because the fast moving and highly conducting hydrogen ions are being replaced by the slow moving and less conducting ammonium ions, the ammonia that is being added reacts with sulfuric acid, giving us ammonium sulfate. Then later ammonium sulfate ionizes to give us ammonium ions. So the ammonium ions are heavy as compared to the hydrogen ions, so they are not as fast. They don't have a fast mobility or conductancy as hydrogen ions, which causes a progressive decrease in conductivity along line AB. Now let's look at the reason why conductivity after the endpoint. This is your endpoint where we had the turning point. And you say that at the endpoint, that means that all the hydrogen ions were being neutralized from the acid, or all the acid was being neutralized. So at the endpoint, you are adding excess of your ammonia solution. Now let's look at the reason for that. Now just like I explained, the sulfuric acid reacts with ammonia solution as we are adding it to give us a salt which is ammonium sulfate. Now what happens, ammonium sulfate, since it's a salt, also sulfurly a strong electrolyte, so that it fully ionizes, giving us ammonium ions together with the sulfate ions. But remember that in solution, these ions are going to be very heavy, so their conductivity is going to be very low, since their mobility is also low. So we say that B is going to be our endpoint, and it's at this point where we have neutralized all the acid in formation of a salt, which is going to be ammonium sulfate. And that means that conductivity at that point is going to be due to formation of the ions from the fully ionized salt, because after that salt being formed, it ionizes according to this equation. So that means that conductivity at the end point is due to the ions that are coming from the salt in each and every graph that you are going to be looking at. So conductivity at the end point, which is B, is due to ammonium ions and sulfate ions from the fully or completely ionized or dissociated salt. So looking at the point BC, where our conductivity remains almost constant, is because the ionization of your excess weak ammonia solution. Now here we are going to go back a bit to ionic chemistry. Now in ionic equilibria, I told you that when you're looking at buffer solutions, we looked at a base buffer together with an acidic buffer, and I told you that whenever we are having a weak base ionizing, for example, if ammonia is our weak base and it's going to ionize in solution, we must get ammonium ions together with hydroxyl ions. But here the key, let's first put it on ammonium ions. But also remember, you had your salt, which was ammonium sulfate. This ammonium sulfate was also giving ammonium ions. Now, since this one is an equilibrium reaction, the ionization of ammonia gives ammonium ions which are already existing, and this is an equilibrium reaction. That means that ionization of ammonia is going to be suppressed or decreased by the already present ammonium ions from the fully ionized salt. So that means that ammonia ionizing to give us more conducting particles is going to be impossible, because ammonium ions that are already present or that are already coming from your fully ionized salt up here are going to be preventing or suppressing its ionization. And I said that we looked at this explanation in details under ionic chemistry videos, under the titration graphs together with buffer solutions. So we're going to say that along BC, conductivity is remaining the same because ionization of your excess weak ammonia solution is being suppressed or decreased by the ammonium ions that are already coming from your fully ionized salt, which is ammonium sulfate. Now, since ionization of ammonia is being made impossible, or is made slightly almost impossible, that means that we are going to have a constant number of the conducting particles in solution, which are just going to be ammonium ions from the salt together with the sulfate ions. That means that the ions from the salt are the ones that are going to be in charge of the conductivity, because molecules cannot conduct electricity. So it's only ions that can conduct electricity, and since ammonia which is being added is prevented from further ionization, that means that we are not forming any other conducting particles. So we are going to remain with the same conducting particles that are from the salt, and that's why conductivity remains almost constant in case you plot that graph. So we're going to say that this makes the conductivity of the hydroxyl ions negligible. So you're going to make a note that using data obtained practically, when a graph is being plotted, your conductivity may slightly increase along BC, but the explanation is going to still remain the same. In case you are given tabulated results, your graph BC after the endpoint may go slightly like this, but you must make your explanation to remain in the same phase, because that will be requiring explanation of how buffer solutions act. Because for you to add more excess weak base and you're already having a salt, it's salt made from a strong acid, you are going to have a buffer solution. And I hope you master that topic very well under my ionic chemistry videos. Now with that, let's look at the titration of a strong base against a weak acid. So a strong base such as sodium hydroxide against a weak acid such as ethanoic acid. Now as we are looking at these graphs, you must have in your mind the idea of buffer solutions and how buffer solutions are being made, just like in the previous graph. So looking at this graph, you're going to be looking at conductivity together with explanation of our graph. So this graph, I messed this up. You make sure that you add the x-axis is in terms of volume of sodium hydroxide added, so you make sure that you add it somewhere and you include it as you're taking your notes. So point A is initially lower because initially we're having excess of the weak acid, and you also know weak acids, they partially ionize in solution, so they give us less hydrogen ions less hydrogen ions in solution, and that's why conductivity is generally lower or initially lower at point A. As we said in the statement that initially the conductivity is lower at point A because the few fast moving conducting hydrogen ions are from a weak and partially ionized acid, which is ethanoic acid. So weak acids partially ionized in solution to give us very few hydrogen ions, which are the fast moving and fast conducting ions. So that's why conductivity is very low, because ethanoic acid is a weak acid. Now looking at why conductivity is decreasing along AB as we are adding our sodium hydroxide, is simply because the few hydrogen ions that are present are being neutralized by the hydroxyl ions from sodium hydroxide. So it's as simple as that. Titration graphs are the easiest to interpret. So you see that conductivity decreases slightly along AB because as sodium hydroxide is being added, because the first few moving highly conducting hydrogen ions from our acid or from our weak acid are being neutralized to form water by the hydroxyl ions that are coming from sodium hydroxide. So what we shall be left with are going to be the sodium ions after them neutralizing, because the sodium hydroxide gives the hydroxyl ions to neutralize your acid, and then remain with the sodium ions, which have a less conductivity because they move slowly, their mobility is low, and therefore conductivity along B is also going to be slow. Now let's look at the point where we are having this increase. We just have a slight decrease, but later we get a major increase. And why is it the case? So looking at that, remember that along your AB, line AB is decreasing. Like I said, you need to have the knowledge of the buffer solutions ingrained with you properly. So along AB, we have added less of sodium hydroxide, but we're having excess of our weak acid. And if you're having excess of our weak acid, and you have got excess of your weak acid, and you have added a few of sodium hydroxide, you have formed a salt which is going to be sodium ethanoate. In other words, you have formed your acidic buffer. So in this buffer, this salt fully ionizes to give us the ethanoate ions together with sodium ions. And these ones also contribute to the conductivity along AB. That's why it does not decrease sharply. But also, your weak acid, the few hydrogen ions that are being present, the reason why the graph decreases is because the hydrogen ions that were released have reacted giving water, or they have been neutralized. So that's why conductivity decreases. So we can make a supplement that conductivity is generally higher, or it's decreasing solely by saying the ethanoate ions that are coming from our fully ionized salt, which is sodium ethanoate, formed are going to suppress the ionization of the weak acid, which is the weak ethanoic acid. Because remember that whenever we're having an acidic buffer, it always prevents further ionization of your weak acid. So it means that the protons that are being neutralized by sodium hydroxide are not being repressed, because the weak acid, although it's present in excess, the salt that is being formed after sodium reacting with part of the acid prevents the weak acid from further ionization, simply because when it ionizes, the salt gives the compound that is already ionizing to form. And since it's an equilibrium reaction that, like we explained, such a reaction cannot proceed. Now proceeding, we're going to say that we look at BC, B to the endpoint which was C. So conductivity is gradually increasing there due to the increase in the number of conducting ethanoate ions. But these ethanoate ions and sodium ions, they're going to be coming from your fully ionized salt of sodium ethanoate. Remember that as you're adding sodium hydroxide is going to react with this weak acid, giving sodium ethanoate. But we say that also it's fully ionized in solution. So as also is fully ionized in solution, that means that they are going to form excess of your ethanoate ions together with sodium ions. So we expect that conductivity is going to be increasing due to the ions that are going to come from the salt. Now we reach at point C where we had our endpoint. Now point C is our endpoint, and we say that at the endpoint is where all the acid has been completely neutralized, forming a salt. So the endpoint is always the ions from the salt that are responsible for the conductivity at that point. So when endpoint is reached, all the acid has been neutralized, and we only have our salt, which is sodium ethanoate. So is this salt, which is sodium ethanoate, that ionizes to give us sodium ions and ethanoate ions that are fully in charge or fully responsible for the conductivity in that solution at that given moment. Now, further than the endpoint is always going to be the ions that are coming from what you are adding. For example, along CD, conductivity is rapidly increasing because you are adding excess of sodium hydroxide. That means that sodium hydroxide is providing highly or fast-moving hydroxyl ions that are responsible for the rapid increase in the conductivity. Now this is going to take us to our titration graph number 4, which is going to be titration of a weak base against a weak acid. For example, if you're having ammonia solution against ethanoic acid. So you're going to have your graph, which is going to be conductivity against the volume of your base, which is your weak base ammonia solution that you're adding. So remember that here you're having your conductivity to be initially lower because you are at point A, you have not added any ammonia solution. That means that you're having mainly your weak acid, which is ethanoic acid, and you say that weak acids partially ionize in solution to give us very few hydrogen ions or very few fast moving ions in solution. That's why conductivity is generally lower at this point. And then if you go to point AB, why we're having a general decrease along AB is because as we're adding ammonia solution starts to neutralize the ions or the fast moving ions that are coming from our ethanoic acid, which has been partially ionized. So you're going to say that conductivity is slightly decreasing along lane AB or along curve AB as ammonia is being added, simply because the ethanoate ions that are coming from ammonium ethanoate are being suppressed by the ionization of your weak ethanoic acid. Remember in buffer solutions we say that as you're adding, for example, as you're adding ammonia to ethanoic acid, you're going to form your salt, which is going to be ammonium ethanoate. So this salt, ammonium ethanoate, the progressive increase here is going to be as a result of your salt fully ionizing solution, giving ammonium ions together with ethanoate ions, and up to point C, which is our end point. And at this end point, we expect that all the conductivity is mainly due to the ions of your salt, which is ammonium ethanoate. But the decrease here is due to the suppression of your ionization of ethanoic acid by the salt that is being formed. But later, that salt that is being formed causes a general increase by it getting fully ionized in solution, giving us the ethanoate and ammonium ions that cause a rapid increase in conductivity, since they are going to be increasing the number of the conducting ions in solution. So making out some equations for that, you're going to have ethanoic acid reacting with ammonia, giving us your salt, which is ammonium ethanoate. Now this salt, immediately is being formed, it ionizes. So its ionization to give us ethanoate ions and ammonium ions suppresses ionization of ethanoic acid, just like we explained that fully in details under buffer solutions. I hope you have come to this video when you have the full idea of buffer solutions. So that's the chemistry that takes place. So conductivity gradually increases along this side, just like I said, due to the increase in the number of conducting ions that are coming from the salt. And that's going to be ethanoate ions together with ammonium ions from your completely ionized salt, which is ammonium ethanoate. Now at your end point, conductivity is due to the salt that is being formed, and is due to the ions from this salt. Because after that salt being formed, it fully ionizes to give you ammonium ions together with ethanoate ions that are going to be in charge of conductivity at that point. Now along CD, we are seeing that conductivity is remaining almost constant. And the reason for that, we say that because your ionization of your weak ammonia solution that you're adding is being suppressed by the ammonium ions already present from your fully ionized salt, which is ammonium ethanoate. Now sometimes conductimetric graphs or titration graphs are not about acids and bases. Sometimes it's about your practicals that you do, and we bring these questions under mixed questions that are requiring you to explain various chemistry concepts. So in this question, you are required to determine at which point conductivity is going to be higher and at which point conductivity is going to be lower based on your chemistry practical knowledge. Remember that conductivity is made possible by presence of ions in solution. So the moment you are forming precipitates, you are lowering conductivity. And the moment you form more ions, you are increasing conductivity. So that's the logic behind this question. So in this question, you are prompted to explain why in the conductimetric titration of your aluminum nitrate solution, again a sodium hydroxide solution, the conductivity of your mixture decreases to a minimum and later increases gradually and finally increases rapidly with excess base. So we explain that according to your practicals. So in a solution of aluminum nitrate, we expect having the cations of aluminium, and you know that these aluminium ions always react with the hydroxide ions that are coming from sodium hydroxide solution, giving us a white precipitate, which is going to be aluminium hydroxide. So initially it's going to be generally, the conductivity is going to be higher before adding sodium hydroxide because we are having excess of the aluminium ions together with the nitrate ions. But as we are adding sodium hydroxide, the hydroxide ions are going to neutralize, or they are going to remove our conducting particles, giving us precipitates. So since they are reducing the conducting particles in solution, we're also reducing conductivity. So that's why initially conductivity is high, but later it decreases gradually or rapidly to a minimum. And that minimum is going to be because all the aluminium ions are being neutralized to form your aluminium hydroxide. That's why you're going to have your minimum. But the minimum is not going to be at 0 because also nitrate ions are present. So nitrate ions will be in charge of the conductivity at that point. But however, conductivity after that minimum is going to skyrocket because now we are saying that the effect of this is because the concentration of aluminium ions in solution is going to be decreased due to complete precipitation. Now the aluminium hydroxide, the increase from the minimum to gradually and rapidly is because the aluminium hydroxide reacts with the hydroxide ions, forming a complex ion, which is tetrahydroxyaluminate 3 ions. Now this one is the one which causes a gradual increase in the conductivity simply because it's heavy. We are saying gradual increase because it's heavy. So this precipitate reacting with the hydroxide ion is giving us more ions in solution. That means that we have increased our conducting ions in solution again. So conductivity gradually increases. But the rapid increase is going to be due to excess sodium hydroxide that is being added. Because the more we add excess sodium hydroxide, the more increase the number of highly conducting hydroxyl ions or hydroxide ions in solution, which causes a skyrocketing in our conductivity. Now you're going to pause the video and you try to take down this question. Now make sure that you try and discuss this question with your colleagues and also try attempting out different numbers to test your understanding. Make sure that you try it out in person. And if that's not possible, you try to discuss it with your colleagues first. Or you try to review the video and you learn how to do all the questions that are lying below it. So pause the video and you take the question. Now this was it for this video. Now you are going to be handling in the next video. You are going to be handling the next session of electrochemistry as a topic, and that is going to include electrochemical cells. So don't miss out on that opportunity. Make sure that you subscribe to the channel and share the video to your friends so that you can all benefit as a group. Join me in the next video and introduce electrochemistry.